Okay, so basically, we'll be talking today about polymer melts. Till now, we have been talking about polymers in a solution. We are typically talking about an one polymer dilute solution, non-interacting with each other. Today, we will discuss about the opposite case, which are called melts. And in the next slide, I'll discuss a bit more about that. And polymer melts at low temperatures get into a glassy behavior. Now, what is meant by glassy behavior? So I have to first discuss that. Uh, what is glassy physics and so on and so forth, and then discuss the phase diagram, how polymer melts behave the when you change temperature and when you change the microstructure of the polymer, how things change and so on and so forth. Another important idea which I need to introduce to even understand glassy behavior is the phenomena of scattering. How do we figure out what is the microscopic state of the system, right? So to basically discuss glassy behavior, we have to discuss something called S of QT, which talks a bit about the dynamics of the polymers. And that I should introduce through the idea of scattering. And the scattering is also used to understand this phenomena of scattering. The scattering physics is also used to figure out how an individual polymer chain in a melt is organized, right? So you can do analytical calculations, but they are typically self-consistent. But you can do simulations and experiments. How do we get to know about the system? So a general idea of scattering is important, even to read some experimental papers. And to that, I shall enter glassy polymers. And at the end, basically, I shall introduce to the idea of correlation hole, which I shall also introduce at the beginning, but talk in more detail at the end. So that's the plan of the lecture this week. So this is Polymers lecture 9 and 10. It will be in 2 or 3 parts, okay, as usual. So, okay. Well, I already told you that we'll be discussing scattering, some glassy phenomena, polymer melt at the beginning and the end, because polymer melt is what I want to intend to discuss about, and the idea of correlation hole. In one word, if I had to say how in a polymer melt, that is in a polymer, so when you melt plastic, okay, plastic is full of polymers, that's solid, and there is no other thing, there's no solution in plastic. When you heat plastic, it melts and becomes a fluid, and that's a polymer melt. And so that's a highly interacting system of polymers, right? So we want to now discuss how those polymer conformation is. We'll talk also about the dynamics, detailed dynamics later in some other week. The first thing we want to say is how are they organized? Because it's a messy, largely interacting system. And the most interesting idea is that the conformation of the individual polymer chain in a melt is an ideal chain. Okay, so it's a Gaussian ideal chain. So actually interactions, multi-chain interactions within and interchain and intrachain, they get cancelled out so that the conformation is similar to that of an ideal chain. This was first realized by Fleury a long time back, but it took some time for people to understand and establish experimentally and so on and so forth. Okay, so so that's the crux, that polymer chains are ideal. Polymer chains in a melt, when the polymer is liquid-like, it's an ideal. And so basically what I have tried to do is give a schematic idea where different chains are drawn with different colors. So what you should think is, just like a solid, when you think of a crystal or something, you think that there are atoms, they're just touching each other, and there is basically space between them. There's nothing in between the polymer chains. There's just vacant space, right? It's just like in a crystal, except here the molecules or the monomers, they're not organized, they're not sitting in a lattice. Moreover, whenever we use the word polymer melts, basically we think of a viscous liquid. Of course, polymer melts at lower temperatures, turn glassy. What does glassy mean? Please wait for some time. The point is there is no solvent in space between monomers. It's all full of polymer chains. Okay, there's nothing in between except vacuum, in intermolecular vacuum, if you like. So that's what is polymer melt. So it's flowy, it's highly viscous, flowing liquid. But basically, it can flow freely over very long time scales, not like that of water, but it's a viscous liquid. They can flow freely only if they are unentangled. So, they can be, I mean, yeah. So, I mean, if you have entangled chains, it will flow much more slowly. If it's unentangled, then it can still flow. And if they're cross-links, then they can flow to some limit, but then they will also maintain solid-like behavior. Okay. So all this will be discussed partially in today's lecture, partially in a later lecture. But the picture that you should have in mind when we talk about polymer melts is something like this, and something which can flow, right? And the first question is, okay, so polymer chains in a melt, are they overlapping? Are they entangled? Is the picture more like this, or is the picture more like this, where basically there are polymer chains touching each other, but each is occupying its own space. They're not much entangled here, right? The question remains, because there is, I mean, they might behave like ideal chains, but they're not ideal. There is interaction, steric hindrance. What is steric hindrance? Wait, okay. Let's use the word exclude volume interactions. Part of chains can't overlap, so that is there. So, and locally, I mean, you might be able to see more monomers around the center of mass of each polymer chain. Now, just to give you the results, basically, if you had polymer chains in 2D so that they can't pass each other, this is the situation that you get. Okay, where basically each polymer has various conformations. It's basically an ideal Gaussian chain in terms of conformation. Okay, I mean, not in terms of that the chain can pass through each other, and as a consequence, in 2D or in confinement, this is the picture. Very sharp confinement. This is the picture which you get. Whereas in 3D, so in 3D, this is the kind of entangled thing that you typically get. Of course, for entanglement, you need extremely long chains. Okay, so you can't have, if you have very short chains, then you're not going to get entangled systems. They can overlap a bit, right? This figure is taken from a very good discussion on polymer melts, is also there in this book by Dichens, which is the scaling concepts in polymer physics. So this figure is taken from there. The other thing which I want to discuss just as an introduction before we go on to more details is, by the way, I haven't proven that it's a melt, because it is calculated that a polymer chain in a melt is Gaussian ideal chain, because it's typically calculated by self-consistent, pretty advanced self-consistent field theories and so on and so forth, where you basically write down the interaction, an average interaction, the effect of many other chains, and then you solve it self-consistently on the computer. Okay, so what we are going to show towards the end is establish experimentally that this chain is ideal. And the other question we want to discuss is, what is the kind of monomer distribution of say this white chain among a mess, among a mess and a mass of other black chains. Okay, so suppose you just focused on one polymer chain. Then about the center of mass of that polymer chain, you would see that the number density of black monomers gradually decreases. Okay, and there is overlap. It's not that there isn't. So there is an overlap over there's a presence of black monomers. Black is just to denote the background while your focus is on the white chain. There is monomers from other chains which overlap, but gradually as you move towards the center, there's a relative depletion of monomers from other chains, whereas there is a higher concentration, relatively higher concentration of uh, monomers of the white chain, and as a consequence, this is the distribution. So this is total. The total monomer density is uniform over the entire system in a melt, but within that you do see a higher concentration of say white monomers here and a lower concentration of black monomers, labeled black monomers chain, right? So that's the message here. That is what I have written here. So after this, to discuss in greater detail, so that's the big picture that you have of the polymer melt. That's how polymer melts are. Before going to the more details towards the end, we will basically discuss a bit of scattering, discuss a bit of glassy physics, and then come back again to polymer melts, because I have to train you with the language which I shall use to discuss polymer melts at the end. So scattering. So whatever discussion I'm doing, it is basically based on Rubinstein section 1 point. There's something in the first chapter, something in the second chapter, the third chapter, and the dynamics in the 8th chapter. What my intention is to do is basically condense the basic physics ideas, not the derivations, into around a next 20-25 minute module, which gives you the physics, how we figure out about polymers. This is not the only method. Scattering is not the only method. There are many other methods, but I'm not the right person, experimental person, to talk about all the different methods. What I shall do is talk briefly about scattering, which is used, and that will give us enough structural quantities, certain quantities, statistical quantities, which is also calculated in theory simulations, and that's how we figure out about polymer chains. Okay, so that's why we are discussing scattering, and I'm condensing it into 20-25 minutes, and not all derivations are going to be there. You can look up the derivations here. I'm trying to give you the crux, the summary of the entire physics. So basically section 1.7.2 in Rubinstein discusses how do we get to know the molecular weight of a polymer chain. Now, of course, here we shall discuss that all the polymer chains are exactly of the same length. That is, there is no polydispersity. Polydispersity means you have different sizes, right? So we shall assume no polydispersity, but any experimental system is going to have polydispersity. You are going to have chains of slightly different lengths, and sometimes you can have chains of very different lengths. So those are details. Those are very important details, but that will be out of the scope of the next 20-25 minutes of the discussion. Okay, so what is the basic principle? We shall talk about light scattering, but the wavelength of light is, as you know, order of microns. 4 to 6 microns is, whatever, 3, red to green, whatever be it, right? So 4,000 angstrom to 6,000 angstrom, or 3,000 angstroms to 6,000 angstrom. And what scattering relies on, we're talking about dilute systems at the moment, is that the solvent and the polymer or the monomer which is dispersed in the solvent, they have different refractive index n or beta in different regions. Hence, different parts of the polymer of the solution, the part where is there is pure solution and the part which has polymer, they will scatter differently. And this scattering differently, the scattering contrast is what the detector picks up. Now, if you're talking about light, we shall the scattering, the origin of the scattering contrast essentially comes from the different polarization of the electron clouds in different parts of where there's pure solvent and where there is solute. But light, I mean, a polymer, when you're looking at a polymer, you could be looking at different length scales, right? You could be even looking at how is a monomer moving or a segment of the chain moving at nanometer length scale. And that, of course, you can't investigate using visible light. So people do use X-ray scattering as well, where the scattering contrast comes from electron density differences in the solvent molecules and the solute molecules. One also uses neutron scattering at even smaller length scale, where the difference or the scattering contrast, the different way of scattering from different molecules come in difference in the atomic nuclei. One also has to deuterate it to find a scattering contrast, but that's a different topic of discussion. So though I shall pretend that I'm always talking about scattering from light, that's how the discussion shall begin. Please understand that as you go to smaller length scales, there could be X-ray scattering. The origin of the scattering contrast is going to be different, or it could even be neutron scattering. And so again, the physics of the scattering will be different. So I shall pretend it's all light scattering. Light scattering means visible light scattering. Of course, X-ray is also electromagnetic waves. In that sense, it is light. But the polarization, the prefactors in the scattering intensity is going to be different. When you have visible light, when you're looking at scattering due to polarization, and the prefactors is going to be different when you have X-ray scattering and so on and so forth. So please be aware of it. So I'm just telling you right at the beginning, but after that I shall discuss. Okay, so let's start with Rayleigh visible light scattering, which is also called Rayleigh scattering. And how does scattering happen from gases and liquids? Just assume that there's a polarized light electric field. Suppose this is the so-called X direction. So you have a plane polarized light, so electric field is fluctuating, is increasing and decreasing in amplitude in the X direction. The By, suppose, is fluctuating, increase and decreasing in amplitude in the Y direction, and it is moving in the Z direction. And then Ex or By can be written as an amplitude cos 2 pi nu t minus Z by lambda, plane wave equation, right? I think, yeah. So you should at least know plane wave if I have to proceed. And this gets scattered in a scattering volume. The light is incident and is getting scattered, is focused in a certain region of space, which we call the scattering volume V. And suppose it is coming and hitting a particular molecule here. Okay, and we set the origin there at the position of a molecule. And once this electric field hits the molecule, this molecule has an electron cloud, as a consequence of which there is dipole oscillation of the electron cloud within the molecule, which leads to scattering at time t dash, say. So what is the message? Molecule, the electron cloud experiences an electric field due to the incoming light, due to which the electron cloud starts oscillating. If it oscillates, the electron cloud, a dipole is induced. So it's a time dependent, because positive, and negative, because electric field is changing. So the direction of positive and negative separation, which creates the dipole, is going to change, and hence it's a time dependent dipole. And the polarization will be some quantity, the polarizability alpha, into the incident electric field due to light, right? And if there's a dipole oscillating, that will itself create a radiation which is emitted in all directions, right? That's what fluctuating dipoles do. And hence radiation will be emitted, and that is what we will call scattered light. And the electric field will be proportional to the acceleration of the charges. If P was the dipole moment, d2p dt2, that's what the scattered, the radiation emitted in all directions will be. It will depend upon d2p dt2, but moreover, the electric field will decay from the origin as the light is radiated out as 1 by r, right? So the electric field at any time t at a position r from the origin will be basically this, but this is calculated at time t dash, because the acceleration was at time t dash. The radiation to reach some point r will take some time. How much time will it take? It will take r by c, right? So basically, the electric field that you shall see at a certain point r away from the origin, I should think that this point r away from the origin, that will depend, its amplitude will decrease as 1 by r, and it will depend upon the acceleration of this dipole at time t dash, which was at a time r minus c before. So if t is the current time, the position of the light wave is here r at time t, then it depends upon t dash. That's, and just to remind you, a lambda being the wavelength and frequency, the product of the two is the speed of light. Okay, so the scattered intensity, yeah. So the scattered intensity is actually 4 pi square by lambda square. Okay, so basically this 1 by c square, if you replace, right? So it's 4 pi square by lambda square, 1 by r, polarizability, incident, because how much scattered intensity, that depends the dipole moment itself. It depends upon the incident light, and when you take that derivative with respect to time, you get these quantities 4 pi square by lambda square, because you have taken a double derivative. These things have come out 2 pi and nu c by lambda, they have come in front of the expression, and that's why you are seeing these extra terms here. 1 by r was there in the previous term as well, and so on and so forth. And so the scattering intensity from one molecule depends upon the time average quantity, E square, the function of time, expectation value, which basically means that if you square this, here you get polarization square, dipole moment, sorry, this is the incident intensity, and you get these extra prefactors, which is called the Rayleigh prefactor, right? So what do you see? The scattered intensity goes down as lambda to the power 4, which you might know as a Rayleigh scattering result, right? And it decreases as 1 by r square. Alpha is the polarizability of the medium, of the molecule medium, and I is intensity, right? And if you have some n molecules, then Is from n molecules is proportional to Cn, the density of the polymer, if you like, right? If there's a solvent, you would have something. If the polymer, then the scattering contrast would depend upon the density of the Cn, which is the density of the polymer divided by, I mean, it's the molecular weight of the individual molecule. So capital M is the molar mass, Na is the Avogadro number. So basically, Cn is the number density of molecules, and that's what the intensity would depend on. Now, as you go from the solvent region to the solute region, polymer region, the refractive index in the solution would change, and that is what would create the scattering contrast. Now, the square of the refractive index is related to the refractive index of the background medium, in this case the solution, plus 4 pi polarizability into number density of molecules, right? So this comes from background electromagnetism, background physics. Okay, so we can't discuss this. Just accept this. And if this, so this is how the refractive index will change if you have some solute molecules with this number density Cn and alpha polarizability. This is the how it would change. And if you take the derivative, right, so if you are asking if we increase concentration, how would this change? How would the refractive index change? Then if you take the derivative, then you can write the polarizability in terms of how the refractive index is changing with concentration. And this is the molar mass, and this is the Avogadro number, but basically this is molecular weight of an individual polymer chain. And this expression for alpha, you substitute here in this expression for the scattered intensity, which depended, of course, about the incident intensity. So you substitute there, and if you substitute it there, what you get is the scattered intensity depends upon 4 pi lambda to the power 4 Rayleigh scattering, r square, n square, and n stands for refractive index square, dn dc whole square, Cn number density, and this Cn in turn depends upon the density in the molecular weight. And if you can calculate the scattered intensity by the incident intensity and normalize it by the r square, right? Because as you go farther and farther, go down, then you get a quantity called the Rayleigh ratio, which is represented by r theta. This is some constant which depends upon 4 pi n square lambda to the power 4 dn dc whole square, and this Rayleigh ratio is dependent upon Cn, number density, which in turn is dependent upon the density, Avogadro's number, and the molar mass. So if you can measure this quantity, the Rayleigh ratio, then it depends upon the molar mass in a linear manner, right? Because you know this constant, you know n and lambda, what wavelength of light you're using, in dn/dc, you can figure out. If you know these quantities, if there's enough scattering contrast, then you know this quantity is going to increase linearly with the molar mass. So by measuring this, you get the molar mass. Of course, as I've told you, I've assumed no polydispersity. Of course, there will be complications if you have polymer chains of different lengths. Okay, so now that's the general principle. Now going over to suppose you're looking inside a single polymer chain. Now consider one polymer chain, and this is section 2.8 of Rubinstein. And as previously, suppose light was incident UI direction, and it got scattered from here, and it got scattered from here, two different, then they move in the same direction, right? And your detector is placed somewhere here. You allow the light to interfere, and if you allow the light to interfere, what you have done is kept the detector as a at a certain angle theta from the original difference. So then the phase difference that you will get, I mean the intensity that you will get will be a consequence of the interference of these scattered light, and that in turn will depend upon the phase difference, which is phi j. The path difference, this path minus this path, this is the path difference, because different light and different segments would have traveled different lengths, different distances, and the path difference will be 2 pi n refractive index by lambda ui minus uj. This is ui, this is uj, right? Into rg. What is rg? Rg is the distance, the vector joining the two points from where it has been scattered, say from this point and this point. So that is rg, and we can write down the phase difference as q dot rg. What is q? Q is ui minus uj, 2 pi n by lambda. So that is the so-called change in the direction, the scattering direction from the original direction, right? And if you're not changing lambda, then basically as you move the detector for different values of theta, q changes. Q can be written as 4 pi by lambda sine theta by, so you can change q by changing theta. Now if the light is coming, electric field is the I mean you have already seen that the scattered light ej is dependent upon ei, the incident light, cos 2 pi nu t minus phi j, and scattering from different points, right? Different molecules, basically you're summing over j, and the total electric field at any point will be ei, the incident electric field, sum of scattering from different points in space. So basically 2 pi nu t ij, summation over j, because j is 1 to n, all the molecules in this system, right? So it's all the different scattering sources, different molecules, different monomers in the system, if you like. So the scattered intensity will be Es intensity. This is intensity, this electric field square, time averaged over one time scale. How much is one time cycle? It is 1 by nu, the frequency, which is the time period, right? And so if you want to do a whole square, there was a single summation here, right? So now you have this summation whole square, so there will be n square product terms, right? So hence you are getting 2 ei incident nu, and all other prefactors are sitting inside here, and you're basically doing a time average from 0 to capital T, and it is this term whole square which gives you, because there will be n square terms now for different values of j, right? Because you have many terms multiplied by equal number of terms. As a consequence, you get ei a square again, then summation over all pairs of molecule, j equal to 1 to n, k equal to 1 to n. What depends is the phase difference between all pairs of molecules. So that's what your final scattered intensity, did scattering from many molecules, depend on. And in this case, you can calculate a quantity called the form factor, which gives you, which will finally give you the internal structure or the organization of the molecule. right? And that depends upon the scattered intensity IQ. Q depends, you remember, at an angle where you have on what angle you have placed the detector from the light which is going straight. So I is 0 is the one which goes straight without any scattering at an angle, right? And IQ is at an angle. So it's the, I mean, you can think of a dipole moment radiation scattered in all directions, but of course in X-ray it will be different. I mean, this factors will be different from that of from that of visible light, where we're using alpha square polarizability. But if you're using X-rays, that polarizability will be replaced by something else. Those prefactors will be different. The values of A will be different, right? But the scattering intensity, which depends upon electric field square, prefactors might be different. Still, it form factor will be defined by ISQ, IS0, right? So basically, IS0 is when the light or the electromagnetic radiation or the neutrons, as the case may be, is traveled straight. And PQ is basically defined as 1 by n square. So it can be shown by statistical physics that this PQ, which is related to the intensity, the ratio of intensities, is actually 1 by n square, k equal to 1 to n summation, j equal to 1 to n summation cos phi k minus phi g, difference in phases between all pairs of molecules. But what is phi k and what is phi j? It is q dot ri minus q dot rj. If you remember, phi j, this was the origin, was ui minus uj, right, which was written as q dot rj, right? So q dot rj. Looking at the phase difference between ri and rj, right? So here it was the origin, hence this rj comes. If you're looking with respect to some other position, what you will get, the difference in the phases from the 2 points will be q minus ri minus rj. That's exactly what you have got here. Sorry, this should be, instead of I, it should be k. And this in turn, and I've not shown you the derivation, the derivation is there in Rubinstein. For small values of q, for small deviations in the angle, small scattering angles, can be shown as, finally, can be shown as 1 minus 1 by 3 q square rg square expectation value, where q itself is 4 pi n by lambda sine theta by 2, right? So what happens is, if you can experimentally measure PQ, which is the ratio of the intensity at an angle theta at a certain value of Q, then that is related as you change Q, right? As you change Q, you can see how the intensity falls, and the slope of PQ versus Q square will give you R squared G. So you get an estimate of the size of the polymer chain, right? And you do it with different polymer chains of different lengths, and you get an estimate of the size of the polymer chain. And then you can get your R squared G versus N relationship. So what do? You again calculate the Rayleigh ratio, which in turn this time is dependent upon K, that factor which has polarizability, and is going to be different if it is X-ray scattering or neutron scattering. And then the concentration, the molecular weight, and 1 minus q squared by 3 r squared g. So if you plot r theta versus q, right? If there's a curve, then the intercept will give you an idea of the molecular weight, whereas the slope of r theta versus q square, you're changing the angle of the detector, hence you're changing q. The slope r theta versus q square, if you plot it, then the slope at small scattering angles and valid for dilute solutions will give you an estimate of the size of the polymer chain. Uh, so for larger Q values, what does larger Q values mean? For larger Q values, when there are more deviation, uh, basically, and then you can probe larger Q also actually means, uh, yeah, then probe larger length scales. Then Debye calculated the P of Q for ideal chains using the ideal chain approximation. Since a polymer can take different conformations, you basically thermodynamically, statistical mechanically average over ideal chain conformations, and then you can calculate PQ, right? And divided it the first and averaging over different polymer concentrations. The conformation, sorry, he found out that PQ is equal to 2 by, I mean, this formula. Okay. So the derivation is again there in Rubinstein. This is exponential fall. Okay. And then it's also 1 by q square r square g whole square. So basically, at small scattering angles, so what I've plotted schematically is PQ, it's again taken from Rubinstein, versus Q r square g average square root. Then from this regime, uh, at the intercept, you can get the molecular weight. In this region, you can get an estimate of r squared g, whereas from larger, I mean, if by chance the expression of PQ fits this, then you know with this expression, if you are able to fit it, because you've got r square g already from small deviations from small q values, and if the rest follows, then you know that you have an ideal chain. On the other hand, if there are deviations from this, and you know how PQ varies as Q, then you might actually get whether it's a real chain or not, Fourier chain or not, or if there are other deviations away from the ideal chain or from the real chain, and so on and so forth. You can basically get the fractal dimension of the object by looking at the power law, how it decays. Okay, so basically, on one hand, you're measuring PQ, which is the ratio of intensities. That's a measurable quantity. And statistical mechanically, it has an expression like this, but it can also be recast. Statistical mechanics, you have to look up books on basically statistical mechanics of liquids. And then PQ, the ratio of the intensities, can also be recast as 1 by 1 upon n, 1 plus integral over all space pair correlation functions g of r. We have discussed pair correlation functions before, and the Fourier transform of the pair correlation function. Okay, so basically this quantity is already a cost. So basically, depending upon the positions of the different monomers, if you statistically average over that, that is related to essentially the pair correlation function, right? And then you're taking the Fourier transforms. This can be recast as the pair correlation function, the Fourier transform of the pair correlation function 1 plus this. And this is a quantity which you can directly measure. And if you have that, you can take the Fourier transform of this quantity and you can get back g of r, right? So another quantity is so-called uh, structure factor, S of Q, right? And that is 1 by n, and is the number of monomers in scattering volume V, which goes n could be from the same molecule or it could be from a different molecule. At the moment, I'm not differentiating, so S of Q would depend upon number of monomers in the scattering volume V. J equal to 1 to n, k equal to 1 to n. Basically, you would take all possible pairs of monomers, and if you calculate e to the power I q dot, if you remember what q is, that's rj minus rk, and take a statistical average over it. This is basically over different conformations of the chain as it keeps on changing conformations due to thermal fluctuations, right? Then you can plot a S of q versus q, where at very small q, which means large length scales, you are essentially looking at the G of R corresponding to how one chain is arranged with respect to another chain, right? But at larger Q or smaller length scales, you are looking at intra-chain correlations. Intra-chain correlations here, it will be some power law, right? It could be ideal or it could be real chain. And this is the smallest length scale, the monomer size. It doesn't make sense to go to smaller length scales. Large U is small length scale, whereas somewhere in the intermediate called the Guinier regime, Guinier, then from this part, I mean, which is equivalent to this part, you get the size of the radius of gyration square average. That's the union ratio. And S of Q versus Q is plotted intermolecular, which is basically comes out from the concentration fluctuation in volume 1 by Q cube. Now, Q is very small, the volume is very large, so you're looking at inter chain scattering. One polymer basically creating a scattering contrast. In between there is a liquid and then there is another polymer. So that interpolymer regime is very small q, medium regime is Guinier regime, and this is intramolecular regime. So I'll stop here and continue in the next module of the same lecture. Okay, so I shall stop sharing. And then also basically switch on recording. Stop.